protocol using the absolute value of the weight with respect to the scaling factor lambda, okay? What is the reason why we said that this one's probably less preferable is it technically performs at lower relative levels of accuracy in terms of final network performance than L2 given weight decay, and L2 is the square, right? So we utilize, instead of that L1 regularization, L2 regularization uses the square of the offset. Now, there is something that combines these two things together, which effectively allows us to do one of the functions that that I sort of described to you as a kind of optional process. But let's just look here again for any of you guys who don't have the strongest background in your L1, L2 regularization framework, all right? Why does L2 regularization not eliminate weights entirely, so it won't actually kill off any of the neurons?
It neutralizes some of the parameters.
It doesn't neutralize them entirely, because
Yeah.
of the fact that it keeps, L2 regularization keeps the network from ever going totally to zero, right?
Yeah.
Because instead of utilizing the absolute value of the weight, which is what the L1 regularization does, that's the lasso, least absolute sum of squares operator. The ridge regression operator, right, describes the idea of trying to maintain or broadly distribute the activations across as many of the features as possible. So it's trying to be more democratic, to treat every single piece of the input fairly, and to try to disincentivize the system from just focusing on a very limited subset of the features in play. Mostly this is because of the fact that in reality, complex systems have a lot of interdependency, and those interdependencies create the distribution of the data across a lot of dimensions. So if we want to try to have the system look for maximum accuracy, it's going to have to look for all of the data that's spread throughout all of the features that it's being trained with. We can notice that there's high correlations in some of those features. So if you have some that are highly correlated and others that are only weakly correlated, what's the system going to do with respect to backpropagation? It's going to incentivize entirely the highly correlated elements, right? It's going to drive down the regression characteristics based upon the gradient of the item that has the highest impact on the output. Whereas the elements that are the minimally correlated, they're going to only get minimally updated, right? But if I push down the coefficients of the larger, most highly correlated elements, it forces the system to spread out and look for information across more feature space, right? It tries to say, let me see if I can tease out some of the underlying integrated processes here. Now, do some weights still end up being relatively large with respect to the L1 regularization? Yeah, you can have L1 weights that are bigger, all right? But only so much as they are justified by the amount of error that they effectively encapsulate, right? So if it can get big, as long as it can make an excuse to you that it's necessary for it to get big, right? Because that's a penalty factor on top of the notion of giving the Lagrangian operation for that particular set of weights, right? This is the degree to which this model captures the variance within the system. This is a strict linearity operator, obviously, but whenever extended out, this idea of the summation of each of the weight characteristics for a given model can say, if everybody has been incentivized from only the most active, only the most highly correlated items being given high values and everything else effectively going towards zero, then we say we've done our best to be able to extract all useful information out of all the data we've been presented with. What can happen with the L1, right, regularization in the case that it's taking the absolute value of the weights, the system will then go, well, technically, I'm going to kind of do the opposite direction of that democratized approach, right, and effectively eliminate anything that doesn't seem to be contributing highly to my outputs, right? But at the same time, it's also suppressing every single one of the weights within the system. So once the most highly correlated elements have been pushed down, then it has to fully justify removing the peripheral elements. That's another reason why the idea that is that they do generally kind of work roughly the same in the beginning process, right? So squishing it down, forcing it to search a larger parameterized area is the effective pursuit of the regularization process. As I described, the idea of regularization in between layers is effectively designed to try to correct some of the problems that can happen with the random initialization of the weights or kernels within the system. That is highlighted by, and I missed kind of this piece in the construction of that statement the last time, it's highlighted by the idea that if you have one kernel that's already well suited to identification of a feature within the system, if you look at the degree to which adjusting that kernel, where it's already sort of closely located, right? You have two different regions of your error function, surface. One of them gets dropped over here, one gets dropped over here, okay? This one's dropped on an edge where it's got a gradient, a real obvious set of adjustments that will improve its capacity towards prediction. The other one over here is in a desert, okay? Everything's flat around it. So this one got initialized into the desert, this one over here got initialized onto the side of the mountain, okay? The idea is that if we regularize them, we try to get the process a little bit more leveled out so that not all of the effort at the reduction in the gradient is going into the one that's giving the best return on investment, right? But we also want to try to push the ones that got initialized a little bit poorly towards something that's going to give us some output. So if everybody is trying to be incentivized to look for as broad of an informational input as possible, the kernels will then produce more useful information over time. But in random initialization, the initial conditions can create two very different networks, right? There's a reason why we said sometimes when we reinitialize a network, we can have it converge to a different output. But with the right set of learning techniques, theoretically that should not be true, right? Theoretically, if we get stuck in a local minima, or if we get stuck on a saddle point, or if we get stuck on a plateau with that gradient propagation process, what should happen? We should be able to synthetically, simulatedly anneal, right, should be able to artificially increase the learning rate for a brief period of time. What happens? If we do the appropriate amount relative to the gradient at the time, we should escape from that local minima and continue down the gradient to be able to find the surface. So if we have the right set of controlling factors that stop the network from effectively getting stuck and not continuing to learn, we should be able to have all networks of all types, no matter what their initializations are, effectively converge to the same ideal at the end point, okay? Now the interesting portion of this is we have not yet seen that to be 100% true, but there are some indications that that is starting to kind of happen as we have multiple different people approaching multiple different models and implementing these multiple different ways of optimizing them, as we see that they're relatively searching through that same sort of space, they're relatively converging to the same set of solutions in the end. So if this kind of fits with the paradigm that we understand on a global level for sort of that universal approximation, we say that adequately parameterized models, right, with adequate degree of flexibility and functional understanding that have been appropriately controlled with respect to the training process should all be able to should be able to converge to a reasonable level of error. They should all be able to generate some reasonable degree of accuracy. Given the fact that we're randomly initializing the system, there is no guarantee that we will always converge to exactly the same solution, because this is not a completely algorithmic solution, right? If it were, it would take forever, right? If it were totally ideal at every step of the process, the calculation requirements for truly deep systems would, as we say, combinatorically explode, right? We can see that very clearly. But implementation of the regularization process is a methodology to be able to try to get the system to stop overfitting, right? So this allows us to do something that we are interested in, all right? What we're interested in is we're interested in creating the most complicated model that we possibly can without going over. This is a complete antithesis to the methodology which we talked about in supervised learning, all right? Traditional machine learning frameworks talk about the idea of parsimony. How do you create the model that is best, the least model with parameterization required in order to accurately describe the system. Deep learning says we're approaching problems that are on such a degree of operational complexity that we need them to be robust, right? They must work in a variety of different environments. So we say, well, neural networks, every time you add a neuron, what happens to it? Combinatorics, like just one neuron in one layer, adds all these additional weights, adds all this additional necessity for calculation. Even one neuron adds a significant amount of flexibility, right? Add a layer, now you have a whole, just all blows up, right? Now think about the idea of a deep model. Layer after layer after layer after layer with kernels rather than single weights operating on these outputs. There are a number of parameters in those systems. If you were to model them as traditional polynomial equations, they're huge, right? Huge polynomial equations. Say, well, this is a totally different approach to what we were doing beforehand. One of the biggest problems we had, and one of the reasons why we avoided it within traditional machine learning approaches, was because too many parameters ended up doing what? Giving the model too much memory. It could remember too many things, and thus what it could do was memorize, right? So when you stop trying to fit, you stop trying to understand. When you stop trying to understand, you memorize. I will give you this analogy. We're talking about a midterm, right? What happens whenever you stop trying to understand and start memorizing? That's when you go try to find like previous keys for the exam, go to all the quizzes, print all those out, and just try to get the pattern between what's the question and the answer pair, right? That's overfitting, right? Psychologically, it's overfitting. Let's diagram it a little bit more. Let's tease it out a little bit more and think about that, how that's happening, why that's happening. Why would you, as a person, be going to that direction, right? Frustration, effectively. I mean this because of the fact that I think you can make an analog in machine learning frameworks that when the model has stopped after a certain number of times of going through the data, it's not getting any better at what it's doing, right? It gets a little frustrated and it starts going, well, if I can't continue to actually understand what's going on, then I'm just going to start trying to see how I can figure out how an individual component of this system might be able to be optimized such that I can remember that singular question-answer pair. We've incentivized it by nothing more than trying to figure out how to totally minimize the loss function operator with respect to weights. It is going to, unless we adequately control for this problem, it is going to overfit. It wants to. It has the necessity to. When we talk about the number of parameters that are available in these models, which in order to be robust to all the scenarios that they must face, have to be highly parameterized, way beyond what we're used to for standard linear integration models, we have to implement things that can stop them from doing that. We have to say, no, matter of fact, I'm actually going to do averaging, I'm going to do pooling and localization, I'm going to drop out some of the components. Okay, we'll talk about drop out in a minute, but I'm going to actually delete stuff, right, so that you can't memorize. So a lot of the tools that we're talking about here with the more robust methodologies for optimization are a lot about following through with telling the system you're going to have to deal with only having part of the picture at any given time. So this is saying that you don't get to have all of the gradient back effectively. Because if you think about what happens here with respect to minimization of the weights as an approximation with respect to the loss function characteristic, as that factor lambda increases, my stochastic methodology for gradient descent propagation does what? Says how much that weight needs to move in order to be able to make that output. If I've now come back with a gradient descent process that says this weight needs to increase by a certain amount, that penalty is fighting gradient descent. It is actively at odds with optimization. This is weird. It's weird, all right? It says you can only learn so fast. Slow your roll, right? Momentum. Effectively, the idea of regularization is telling momentum to slow your roll. Don't get so crazy that you overlearn or overfit to something. This process of elongating it is really interesting. And I went to a presentation last year by a guy who was another PhD in machine learning, and he was coming to talk about, I think maybe he was looking to be a faculty perhaps, I'm not sure, I don't think he's coming, but it was a good talk anyway. He was talking about this idea that there are certain periods of time within the training paradigm of the model in which the model is most receptive to actually learning. After a certain point in time, what do we have to do with it? We have to stop it from doing any more optimization because we've said you've gotten as much out of it as you can relative to your parameterization. So we said you have actually too much capacity to memorize. So we're going to let you do whatever you can do for a while, incentivizing you with the process of constraining your potential for updates. But then we're going to limit you in terms of how long you get to look at the data before you effectively have to stop. Because if we keep letting you look at it over and over again, what's going to happen? You're going to find some patterns within it that you can memorize as well. So even with these regularization constraints, the system will still find a way to skirt that limitation and rule, right? You can only constrain this particular animal for so long. So the mechanism that we talk about here later on is something that we call elastic net regularization. This actually is interesting because this elastic net process is pretty common now, right? It's pretty common now where we have a factor component with the L2 regularization as well as a factor component with the L1 regularization incorporated with one another. So we have two different factors, lambda, that allow us to fine-tune control between whether or not we're just going to penalize large growth rate operations as well as the opportunity to totally ablate neurons, okay? So if L2 regularization pulls it down towards 0, even with a small factor of lambda, what happens? They go ahead and get pulled all the way off. If they get pulled down so small that the L1 factor can delete the remainder of the weight, they can get eliminated. So this keeps the capacity for eliminating the network and eliminating elements within the network, okay? I'm going to talk about with you guys something that I mentioned one time. There's so much stuff in this material. There's just so much stuff, constantly so many things, okay? It took me, seriously, truth be told, it took me years to get the things that I know about this, all right? So I'm trying to figure out how to put years worth of my experience and work time with it into a matter of a few months, okay? So that's the challenge. But why would it not be the case that the fully connected network would always be superior? Anybody think of a situation in which you could think about the fully connected network not being the best, right? If I have one network that everything's connected, and I have another network where some of the elements have been removed from the system, which of those do you think is going to perform better?
Which is less connected?
The fully connected one, right? You say the one that's less connected, okay? You're correct with caveat, okay?
Yeah, I know.
There is a degree to which you can remove stuff without losing too much, all right? Most of the time, fully connected network can be constrained. But here's the interesting component. Neurological networks within the human brain actually start off as relatively fully connected. Then they are successively reduced in their connectivity over time. You guys know what happens when you don't activate a neuron for a long period of time? It dies, right? So explain to me why that would be preferable. Why wouldn't we just keep them all awake? That's the fully connected network, right? That's the one that has all the components integrated with it. So what are we getting out of the process of reducing or eliminating neurons that are not adequately contributing to that particular solution? Efficiency. Structural efficiency. So a reduced network, one that's also called sparse, is actually capable of operating, right, with a degree of increase in qualitative efficiency. Now, this requires that there actually be some level of removable components with it, right? That if the weight connectivity between the elements is removed, what happens to a neuron if all of the connectivity to it is removed? Well, then it effectively dies, right? It dies off because if there's nothing coming into it, there's nothing to calculate, there's no forward prop, And there's ultimately going to be no backprop as well, because nothing that's coming out of it is going to be activated. So when we fully delete or fully remove a single neuron from a system, we can either do so selectively, or we can do so via process of activation. So I'm going to talk to you guys what I mean by process activation here. All right, so dropout-based regularization is a process by which we will selectively remove neurons from the network. Partially, this actually indicates something that is also designed to do what? It says regularization up there on the top. How have I regularized the network? You're seeing the world through keyhole, okay? The lack of being able to see the whole picture at the same time forces you to figure out how to focus on what you actually can see at a given period of time. So by selectively removing elements that are giving you the whole picture at once, it stops you from memorizing. So it's a mechanism of stopping you from memorizing, because if you can't see everything at once, only the things that you will see at any given time will actually give you functional information. Since not every piece of information is perfectly aligned in the same bin or the same spatial process, right? If I selectively remove components as the information is being propagated forward, it actually requires that the identification power that was previously invested in these neurons, right, what happens to it? It has to be taken over by the neurons that are adjacent to it, right? They take on the burden, these take on the burden of what all of those previous feature systems were. So fewer neurons are now participating in more processes, right, relative to the selection power and the feature selection power that is invested here. It forces the network to route the data and components of the data through these selected network elements, such that I can't fully reconstruct the input. This is something that networks can do, right? We can actually see the reason why they would be able to. If I were to say the output of this system, right? If I was totally able to backpropagate the relationship between the input and the output of the system by understanding how the weights compose that relationship between the two, right? The system would effectively be able to, for any given output, right, relative to the activation functions as it's gone forward, to be able to almost tell you what was present at the first layer. This is actually something that we utilize for fully connected systems. We unfold the network once it's been trained, turn it around backwards, input the class of preference, input a little noise to the additional parameterizations, and what do we get? A generative network, right? So once enough inputs have been put through the network during the training process, effectively, you can look and see that the system will have a perfect, almost a perfect link of the order and configuration of the input space embedded within the network itself. So all of those weight parameters becomes a type of memory, a type of functional approximation of the understanding of both the composition of the input as well as its relationship to the output. By giving the network so much memory and so much processing space, it allows it to do kind of crazy stuff, right? So by selectively removing or selectively dropping out components of the space, we stop it from being able to actually build the map from the output back to the input. So without that full map from output back to input, we force it to sort of shove the data through a smaller hole, right, and then blow it up back on the other side. And if we sort of jitter around which segments we're shoving it through, it stops it from ever being able to have a perfect one-to-one map between input and output, which effectively stops it from memorizing. Yes?
I had a question back on the elastic net regularization.
Yeah.
Like, I'm having a hard time understanding, like, if we have that L2 term still, how it can still go to 0 if we have this non-zero term.
Oh. So look here what we're actually looking at. This is going to be the value that we're approximating relative based upon what's backpropped to the weights, okay? So this is our error function. So our total error process, this is the regulated error, right? So the regulated version of the error output. It's going to be based upon the calculated error, the distance between the output and the desired output, right? This is the actual error, right? As well as adding on a penalty coefficient, penalty factor. The penalty factor just takes the summation of the weights and then multiplies that penalty factor by lambda, right? So this is just a number, a whole scalar that gets added to error, okay? So the reason why I say that these force the weights down is because once that penalty factor gets added to the error component, this becomes actually how we do the weight update process, right? This is what we propagate through the network in order to actually get our backprop. So we have two different sets of scaling factors, right? Where the first scaling factor will concern itself with the squares of the weights of the system. So if this one's a little bigger, this forces them towards zero, okay? We can also have a smaller rescaling factor that's present based upon the remaining absolute value of the system, right? We usually make this a small number, which means that it's going to take off a little bit more, a little residual of what's in place here. So the elastic process is saying how much, how strictly, how quickly I'm looking to try to remove regularize. This one will never go to zero, right? Because as smaller number becomes smaller number, it will become even smaller number, right, for the actual error, okay? So it's contributing to error by, if the weight is 0.1 times 0.1, right, then it adds that factor to the error. This one says the whole error, the whole value times lambda gets added to the error. These don't actually go and individually force a specific weight down towards zero. They collectively incentivize the network to push things down because it's collectively incentivizing the reduction of the total regularized error. Right, the total, this is the portion, I said this is the portion we backprop with. This is the one we calculate as the actual output, right? And then this is the one we backprop with. This is the reason why we say we lose something in this translation. We don't get the whole gradient back, right? Because we don't get it because we're actually not encouraging the network to try to reduce by that total amount at any given time. Did I get your question? Do you have something else?
So
I'll stick here as long as it need be.
it's on the other slide, the one after.
Oh, yeah. Okay.
So
Did it get you?
That helps,
sure?
yeah, that helps.
Okay. It's a little complicated, right? But at the same time, having both in play and be able to mess with each, it gives you some advantages, okay? Yeah.
and I guess this is an implementation question, but so if the point is like, part of this is optimization as well as like preventing overfitting. If this is a matrix and you're removing components from the matrix, are we just setting those to zero? Or
We're actually setting them in NANDs in most cases.
okay.
So from a strict
So they don't get
implementation
calculated.
collection, they get put in NANDs because then they don't even get calculated, right? So the moment the system goes and tries to calculate the value, it's saying, there actually isn't a neuron here, right? So it goes to backprop and says, wait, there's no value in the matrix here. So it actually skips it. So most of the time, the optimization functions in the runtime will actually consider NANDs non-ops, right? So it'll just count it as a non-op. Or even if it does pre-optimize, it'll go through and create a sparse matrix version of it, which is dimensionally compressed, such that the calculations get reprojected back into the full scale matrix with the NANDs in place. Do you get what I mean by that?
Yeah.
Right, so I crunch it down based upon the same way that we did with the pooling sample process, effectively calculate that one, and then remap the outputs back to the full one that has that separates it back out into its spatial equivalence with respect to the connected network. Oops. There's a desk here. Who moved this? Come on. All right. So the last thing I wanted to talk about is with this one, and we'll talk a little bit more about some others, but I may actually just let you guys go a little bit early today because there's parts of me that want to like totally keep going and just ram everything through, but there's also parts of me that says, okay, well, we'll get started on it again whenever we come back. That's always the difficulty about this time is I know that anything we talk about today is going to be like 18% absorption, if not less, right? Because it's 2 days before the break. It's just, it's not going to resonate. Whenever we're doing dropout with regularization systems, one of the interesting portions that can happen here is that many batch processes can be effectively treated with different selected dropouts. meaning that those dropouts do not actually have to be total removals of the neurons. They can just be masks relative to the input. So we can either choose to selectively drop out during a specific mini batch certain elements of the system, right? So the dropout process here indicates that during the first mini batch, we randomly dropped out some components, right, of the order here. So there's like 5 elements. So we're going to bring these 3 through, right? And we've dropped these elements in the calculation, so we're forcing that through these, right? The pathway through the network that is taken relative to each of the system structures for the mini batch has a slightly different network, right? Different architecture relative to the mini batch that's being trained with if we're using randomized dropout. This is kind of a really weird thing, okay? The reason why we do this is because if we kind of, you guys ever done an eye test, right? It's like cover your left eye, okay? Now cover your right eye, okay? That's what you're actually telling the network to do, right? You're saying, all right, in this one, cover this one up, okay? And then do the process on that one. And now cover the other side, okay? Now do the process over here. It creates a little bit of a robust perspective because of the fact that part of it is masked and it requires it to go through a different set of processes and protocols in order to find the solution. It forces it outside of its comfort zone. So it would normally, when I have its perfect stereo vision, right, be able to generate the output value that's totally ideal. But it also can do what? Converge to the solution and totally bypass it and overfit to it very quickly. So we want to keep training it. Here's the interesting portion of it. We want the network to stay alive as long as possible. That means that when we start the training process, we want it to keep learning. We want to elongate the learning curve as much as possible. Sometimes we do that by reducing the learning rate, right? That says, don't change your assumptions too much based upon too few samples. Sometimes we do the regularization, right? Don't even adjust the parameters beyond a certain limit because that's just too aggressive. Sometimes we drop out, in which we say we're going to totally mask the system. Normalize within the layer framework. Don't let too much of the information forward between layers. All of these mechanisms are tools that we can utilize to try to draw out the period of training. What drawing out the period of training does is it forces the model to learn from more examples, right? Because it can learn everything it needs to memorize from only a few examples, and then the next samples that you push over it, right, it says, no, I don't really need to do any better. I'm already getting perfect fits on my training data, right? So when you try to expose it to test data, it says, no, it only knows how to make a perfect copy of the training data. That was the only thing that it optimized for. So we talked about mini batching, right? We said, only show you a small amount of the whole data at once. Now we're also talking about dropping out from respect to those batch data, right? So we're saying, not only can you only see a certain amount of them, but you can only see a certain segment of a certain amount of them, okay? Eventually, we're just gonna be passing notes under the door, okay? We're just gonna be like, here's some ideas on what the data set might look like, you figure it out on your own, okay? That's where I say that's the most aggressive kind of mindset behind it, is like, how do we get you further away so you're only making decisions based upon a small amount of information? This is the element that makes kind of the most fun part of this for me, because when I think about what happens when the network is learning to be able to find common features within the data, by mini batching and dropout, you're saying, okay, here's a sample, but here's only one small corner of the sample and another piece down here and another piece down here from this sample, all right? Then the next time the batch is recreated, it recombines that sample with another one, and then chooses to show different segments to the network that time and says, okay, now what can you tell me about it? Effectively, this enhances how many number of samples we effectively have within the system, right? We said the more samples, the more robust we become, the better generalization understanding we have at play. So within image networks, I get a real good picture in my head that, like, I'm going to show this portion of the ear of the person, you know, the top portion of the, and then like this portion of the jaw down the bottom, and say, okay, is that enough for you to be able to tell who this is? Right? Say, well, if not, hold on, we'll go through it a few more times, and then you can contextualize what you think is around it. This idea of being able to take small regions characterize a small region and sort of extrapolate the relationship between the components of the system in that way forces the system to have to spend more time learning a more complex and more robust understanding of the full feature space at play, right? So anything that we can do, any possible mechanism that we can restrict the capacity of the network to fit to exact inputs is going to be an advantage for us in some respects. But take also the consideration that it's going to take longer, right? So the whole point, if we want to stretch it out, right, what was the point to stretch it out? Make it generalize. Make it learn more information from more samples. Keep it learning longer. Don't let it get frustrated and start memorizing, okay? So we say keep it learning longer means it also has to learn longer. What does that mean? It takes us longer to get a good model. So everything that we do to regularize, everything that we do drop out, everything we do to minimize learning rate or optimize learning rate based upon momentum, those things will ultimately cause the training time to get pulled out more. But what we're hoping for is that period of time where we have to do the early stopping, if we shift it further to the left, what happens? If at each epoch it's still learning a little bit and the testing has not diverged yet, it's still learning the general concepts. So the longer we can keep it forced to having to learn more general information rather than being able to switch over to specific information, reducing bias, right, and increasing variance at that point in time, every time that we keep within the training paradigm a small incremental adjustment based upon as broad of amount of information with respect to the distribution as possible, the better that potential model could be with respect to its convergence toward an ideal and robust solution. But like I said beforehand, the cost of this processing continues to go up, and it's become a very real portion of the cost of training large, deep machine learning models. And I think you guys can understand why. Because when you have billions of samples or millions of samples, like 14 million samples, right, within ImageNet, but billions of samples within, RCOS and some of the other big image training model networks, you have hundreds and hundreds to thousands of hours being spent per iteration through that data set, okay? So if you're dropping out during that period of time, that means the model isn't learning everything of value from every image in the data set. It means you're going to have to iterate through that data set many, many times, hundreds of times. So you have hundreds of hours, hundreds of epochs, right? You switch from having to have, hours to weeks to years in order to be able to actually converge to a solution. What do we start to look like? More like humans, okay? Humans take a long time to learn concepts. So part of the system is attempting in some respects to model how we think about things, because we tend to generalize. We tend to express and try to elongate our processes. We tend to try not necessarily to memorize, but to understand, all right? Now, interesting portion of it is education actually flips that paradigm on its head. It incentivizes us to memorize factual information, right? It incentivizes us to get the right answer. But in reality, the most useful skills are those that apply to a broader base of information. So what do we have to do? We have to say, how can I learn something from this experience that generalizes to more space? Which means that every single thing you learn, every single experience you have, is not actually going to be able to change your entire paradigm, right? You can't take one single experience with one single circumstance and let it reshape your understanding of life. So you have to have a composite such that every experience you have, because we don't get samples, we don't get epochs, right? Humans, we don't get to train in that way. But every day is an epoch, right? Every day we learn some things, we have some experiences, we see whether or not what we expected to happen was what we got. But we are incentivized by our neurological chemistry to not overemphasize any individual experience, right? But we're also trained to learn something from it of value. So the more out of sample the something seems to be, the more crazy it is, right? Sometimes it will take longer to process it. But the more mundane something is, the less relevance and utility it has for us. We're going to talk a little bit about recurrent networks whenever we get back. Like I said, a little bit. We'll talk about quite a few different recurrent styles. But one of the things that's encompassed with that is the quality of information that you gain out of a specific experience is commensurate to how different it is with respect to the information you already have, okay? I think I might have mentioned this early on, but one of the interesting things about the way the brain encodes information is that it does drop out. It does have sparse encoding. I'll give you an example. Do you remember how you got to campus today? It's such a regular process, it's such high frequency process that you don't actually memorize that flow, right? The reason why is you've already done it once. And the brain says, I already have a pattern encoded for that process. Why do I need to keep another copy of it? So we have to be able to actually create that incentive structure that stops us from memorizing every single example and generalizing to higher level representations. You can remember a trip, a generalized concept of your trip from your house to school, and it's effectively a reassemblage of each of the pieces that represent that transit from home to campus. But imagine that you have some kind of crazy experience on the way to campus, right? You're going to remember that one. It's going to be unique. So that's one of the capacities that some of these models with recurrence have to be able to take into consideration that's slightly different from these standard feed-forward models is they have to be able to not only recognize where a particular sequence of information or a particular feature sequence is incorporated, but also to be able to determine how it's different from and what the utility of its difference from the remainder information is in order to create a broader baseline. So if our goal as deep learning engineers is to better improve our understanding of machine learning as well as to also improve our understanding of ourselves, right? This is our mirror to our mirror to our soul, as these are a replication of our mechanisms of thought. Then the techniques and tools that we utilize and approach to them should be reflected. It should mimic our own ideas and processes. So from here on out, right, for the remainder of the semester, I'm going to try to focus more on distinct practical implementation characterization, right? I'm going to try to say, show you what the structure is, show you why these things got selected, etc. Not always is that going to make 100% clarity for you, because some of these things took as well years and people and thousands and tens of thousands of hours to train and work. Also, some of them don't make total apparent sense in how they actually operate. All right. Similarly to the reason why we say those internal encodings in convolutional neural networks don't line up perfectly with what we as humans would think were the most important components as a framework. So there's a divergence between the way we think internally and the way the machines are thinking now, right? But that's not a limitation for us going forward. The more we understand how this stuff works, how do you think all of the new stuff that's getting built is coming out? People are recombining this stuff, right? They're taking these constructs, they're building their own network, and they're saying, maybe if we do it in this order, maybe if we recombine this, maybe if we change the incentivization function or the loss function, or maybe if we add a new penalty that changes this parameterization, they can create entirely new paradigms, okay? Find one new loss function approximator, find one new optimization function, and you can potentially transform the entire space. So the reason why we're trying to learn the small little ins and outs of what these small parameterizations within the system do is so that later on, if you go and you say, hey, it's overfitting, or it's doing this, or I'm having difficulty with batch sizing, at least you'll have some framework to be able to understand what, kind of where it came from, what's going for. But we'll talk about specifically kind of how these parameters are selected. So as I mentioned, I think I mentioned one time I was talking with Cheyenne, you can build a network to change the hyperparameters of another network, look at multiple different training iterations, and then actually utilize that. So you have networks that look at networks that look at networks, right? It's networks all the way down, right? So I will follow up with you guys, try to construct not only the review framework to be able to tell you what the topics are going to be covered, try to figure out what slides are highlighted, give you a few examples of some of the problems we're going to be working with, and maybe try to create an assignment that goes along with the concept of the review framework, right, for the midterm. So that gives you incentivization to get it done, as well as trying to get us up to speed on some of those alternative training methodologies, okay? I know we've got a lot to do, right? We've already done a lot and we've got a lot to do, but I think that it's ultimately, I feel good about it, okay? I feel like everybody's, at least for the most part, those of you who are putting in the effort into the assignments are looking like, you're getting the gist of it. From here on out, I want to try to see if you can start doing a little bit more stuff on your own, okay? I'm going to stop holding your hands so much. I'm going to let you explore, let you build your own code, let you find your own code, and let you implement a little bit more on the fly, okay? So talk to me if you need something along the way, and I will try to see what I can do. Obviously, it's not a break for me over spring break, but I'll put out material for you as it comes along, and if you choose to engage with it, then by all means, but no obligations until we get back, and then we'll try to have, get back to work, all right? So enjoy your break, and do as much or as little as you feel like, all right? Rest if it's needed, and work if you need to get caught up. And I'll see you back here in, week and a half-ish, okay? So whatever that is, half the week in Tuesday in 2 weeks, okay?